crystal lattice. What is crystal lattice? Crystal lattice is nothing but three-dimensional regular array of particles. Three-dimensional regular array or arrangement of constituent particles. Constituent particle means either it can be an atom or a molecule or ion, whatever the crystalline solid is. If it is metallic crystal, it is atoms. If it is ionic crystal, it is ion. If it is a molecular crystal, it is molecule, and a covalent crystal, again it is atom. So, here when a particle means any of this, by which the whole crystal is made, right. Three-dimensional regular array of particles. For example, if you take the case of carbon, in the carbon atom, you know that in the graphite and diamond, in the case of diamond, carbon atoms are arranged like this, and this and repetitive arrangement in all the directions. When you extend it, then large polymeric like substance, whatever that is formed with a certain definite size and shape, with a definite size and shape, whatever finally we get, that is particularly what we call the whole lattice. It is like a wall. Lattice is nothing but considering after arranging one brick over the other brick in three-dimensional, then it will form like a bridge, or it will form like a divider, or it will form a wall. So, that whole wall that is formed by different number of bricks is what you consider it as a lattice, right. Then what is a unit cell? Unit cell is the smallest part of lattice. Smallest part of lattice which on repeated arrangement will give you forms the whole lattice, which on repeated arrangement. For example, if you consider that this is a lattice, then the smallest part of it, that is one square, this is a two-dimensional. Here what we are drawing is a two-dimensional array, but normal crystal is a three-dimensional. So, for this two-dimensional, if you consider this whole thing as a lattice, two-dimensional lattice, then one particular square of this lattice is what you consider it as unit cell. This is unit cell. So, unit cell is the smallest part of the lattice which on repetitive arrangement will form the whole lattice. Now, in this, if you look at it, we have blue color or orange color circles. Each one, if you consider to be an atom or a molecule, that is the constituent particle. Blue colored ball is one particular atom, orange colored ball is another atom if you consider, like are two different ions like sodium ions and chloride ions, like that also you can consider. Then that whole arrangement is nothing but the lattice. Now, in that particular square two-dimensionally, now which is connecting two blue colored balls via one orange colored ball, from one blue colored ball to another blue colored ball, is that square what is drawn is the unit cell. This unit cell and repetitive arrangement will form the whole lattice. This is the whole lattice. Now, in this, either the unit cell can be formed by taking from one blue colored ball and going to another blue colored ball, but it should be continuously drawn without any gaps in between, because the repetitive arrangement of unit cell should form the whole lattice. Like here we are taking what you call the blue color atoms as the starting point, right. Then in the next case, not necessary the balls, even the space like this also we can consider to define a unit cell, because if you are defining a unit cell, the main characteristic reason to define a unit cell is that you are taking small part of the lattice and the properties you are defining by taking that particular unit cell. As a result, we are able to understand the properties of the whole crystal. It is something like whether the rice is cooked or not. To check it out, we take 1 or 2 rice grains and just we test it, and based on that we assign the same property to the whole bulk. Similarly, if you are assigning a particular property to a unit cell, that is the smallest part, same property should be applicable to any part of that lattice or whole part of the lattice, right. Now, if you are taking the space, then the unit cell can be defined, the whole lattice can be defined like this, but definitely the unit cell cannot be like this, because you are deviating that starting from a blue and dividing, making a boundary at orange color, which doesn't make a which doesn't give you a uniformity in the boundaries. So, this cannot be a unit cell, right. Here the unit cells, the other way is the unit cells what we are drawing are not uniform. The reason is that in one unit cell it is starting, if you are starting a unit cell considering one blue colored ball, in another unit cell you are starting it by taking orange colored ball. So, that is not uniform. The unit cells are not being considered, not being taken uniformly throughout the lattice, right. And also, as I already told, there should not be any space left. Now, if you consider this, between one square and another square, there is a space that is left in between. So, this again cannot be a unit cell, because repetitive arrangement of unit cells one after the other should form the whole lattice, but here as there is a gap, they are like independent squares, but collectively they are not making the whole lattice. So, that cannot be a unit cell, right. Now, we look at what are the types of unit cells. Types of unit cells basically meaning is the geometry of the unit cells. What are the, based on the difference in the geometry, like in the previous explanation, in the previous slides, what we have seen is the square in a 2-dimensional square unit cell is what we have considered. 3-dimensionally, that you can speak as cube. So, like that, and the, as you know, in the chemistry subject, so far we must have learnt crystals of the type cubic crystal, monoclinic, triclinic, hexagonal, tetragonal. These are the different names what we have learnt for different elements, especially when we deal with their allotropic forms. Accordingly, the geometry of the unit cells, based on which the whole crystalline substances have been classified into different shapes, are 7 different, based on geometry, 7 different geometries have been identified. They are cube, tetragonal, hexagonal, monoclinic, triclinic, rhombohedral, so like this cubic, tetragonal, hexagonal, monoclinic, triclinic, rhombohedral, like this they have been classified into 7 different types. Again in this each type of this geometry, based on the position in the, based on the difference in the position of the atoms or ions or molecules, that is particles, at what position, like for example in a cube, suppose if you consider that this is a cube, then whether all the atoms are placed only at the corners of a cube, if it is so, then we call it as a simple or primitive unit cell. So here what we have is simple or primitive. Simple or primitive unit cell based on the positions at which the atoms or ions are placed. Here the atoms or ions are placed only at corners, right? Then another possibility, now what are the other different possibilities where else the atoms can be placed? The atoms, besides this 8 corners of a cube, other possibility are that one atom if you place at the center of the cube, that is what we call body center. If you keep an atom or ion, that is a particle, if you keep it at the center of the body, then we call it as body center. We call it as a body centered cube. Simple cubic or primitive cubic, where the atoms or ions are placed only at corner. Body centered means corner plus body center. Along with the corners, 8 corners, one atom or ion, that is a particle, is also placed at the center of the body. Then third possibility is, instead of this at the body center, of course, let me make it very clear, with like what all you know, without having an atom or ion at the corner, no geometry will exist, because the basic position required for any geometrical figure except spherical or something like similar types, wherever we have edges in any geometry, in any geometrical shape or figure, the minimum requirement for a geometry to form is, when you have an edge, also you should have a corner. So without a corner you cannot have any geometry, right? So that is the minimum requirement. That is the reason we call this as simple. Then along with the corners, second one what we have seen is a particle is present at the center of the body, only at the center of the body, that is BCC or body centered. And the third one is, instead of at the body center, different atoms are also placed at, suppose if you consider that this is a face of a cube, then one atom or ion is placed at the center of the face, at this center of the face, at this center of the face, at this center of the face. Like that, if you keep, a cube will have 8 faces. When cube has 8 faces, at each center if you keep one atom or ion, then it will become face center. Face center. Face center means along with the corner, atoms or ions are also placed at the center of each face. This is third one. Then fourth one is end center. This end center is only in specific, in the cube it is not correct, but end center means along with the corners, atom or ion is placed at any 2 opposite face centers. Anticenter means corner plus any two opposite face centers, like this, any two opposite face centers. So these kind of 4 types of unit cells. In each geometry there is a possibility, first of all, in any geometry one definite type of arrangement is simple or primitive arrangement, without which no geometry is possible. So this is the, out of the 7 crystal systems, these are 7 crystal systems. Of all the 7 crystal systems, each one again will have different types of arrangement. For example, in the cube we will have these 3. This is simple cube, body centered cube and face centered cube. Like this, in all the arrangements we will have either 1 or 2 or 3 different types of lattices. All these together and all mathematical calculations, geometrical considerations, on total overall, by taking all geometrical possibilities, 14 types of such lattices are found to be exist, and they are said to be Bravais lattices. So these Bravais lattices are 14 in number. What are Bravais lattices? 7 crystal systems, 7 basic crystal systems, in which the arrangement of atoms in each case are different. In total, all put together, it is 14 types. But it does not mean that each crystal, each geometry will have 2 types of arrangements. It is not an average. In many cases, it is only the primitive is only the possible. But in the case of, as I told, in the case of cubic, there are 3 types that are possible: simple, body center, face center. Like this, we will have 14 types of Bravais lattices. First of all, what are the characteristic features of the 7 crystal systems? Means, what are their edges and what are their angles? Means, like in the case of a cube, what are the edges? Means, you have 12 edges, and along the 3-dimensional axis, if you take, if you consider that A, B, C, then A equal to B equal to C in case of a cube, right? Like that is their physical measurement about their edges. And angles, alpha, beta, gamma. Alpha, beta, gamma, if you look at it, then in the case of a cube, alpha equal to beta equal to gamma equal to 90. A equal to B equal to C, A equal to B equal to C, alpha equal to beta equal to gamma, that is their angles. So like that, for each of these geometries, what are their relations in the lengths, edge lengths and angles, and again in that each geometry is can be classified into how many unit cells. That now in the next slide we are going to look at it. So the unit cells exist only in 7 shapes: the cubic, orthorhombic, rhombohedral, tetragonal, triclinic, monoclinic, hexagonal, monoclinic. These are the 7 basic crystal systems, right? Then in this our syllabus, what we mainly interested is on cubic and hexagonal. Remaining are just only for the sake of information only what we require, but in detail what we have to discuss is about packing in cubic crystals, packing in hexagonal crystals, their characteristic properties, geometries, all this in detail we have to discuss. Now, as I told that what are the different intercepts and angles in each type. Now, as this is, if you consider that the intercepts A, B, C and the angles alpha, beta, gamma. Now, the different shape crystal systems and lattice parameters, that is crystal intercepts and crystal angles. For cubic, as already told, it is A equal to B equal to C, that means all the 3 sides are equal, and angles, all the three angles alpha, beta, gamma are equal to 90. Now the second is orthorhombic. Orthorhombic, in orthorhombic, the three edges, the length of the three edges is not same. A is not equal to B is not equal to C, but alpha equal to beta equal to gamma equal to 90. So there is, it is like this, right? One is like this, one is like this, that is orthorhombic. Then rhombohedral, A equal to B equal to C. That means all the three intercepts are equal. All the three intercepts are equal, but the angles are also equal, but none of them is equal to 90. Alpha equal to beta equal to gamma, but nothing is equal to 90. But all three of them are equal to one another. That is rhombohedral. This is in mathematics. Most of you must have learned about these geometrical figures in the geometry concepts. Then tetragonal, A equal to B, that means only two edges are equal in length, the third one is not. But the interstitial angles, interfacial angles, crystal angles means interfacial angles, like this, if you consider it as a face, then this is 90, right. Next is triclinic. In the triclinic, none of the intercepts are equal and none of the angles are equal. Interfacial angles are not equal to one another and none of the interfacial angle is also equal to 90. All three are different and they are different from 90. The next is hexagonal. That is A equal to B, that means two intercepts are equal, but the third one is not equal. And similarly, two interfacial angles are 90 and one interfacial angle is 120. Then the last, the monoclinic, like here monoclinic sulfur, triclinic sulfur, this what we, in the case of sulfur we learn monoclinic and triclinic. So in the monoclinic, A not equal to B not equal to C means all the three intercepts are different, and but two angles are identical, that is equal to 90. The third one is different, not equal to 90. So these are the 7 crystal systems, right? And as I told, there are 4 possible ways of arranging atoms in any unit cell. There are not more than 4 ways. What are the 4 ways then? The primitive, as I already told, face center, body center and edge center, right. Then what is primitive cube? So this primitive cube is, this is what is primitive cube. This primitive cube, as we can see, that the atoms are placed at the corners of the cube. At each corner we have one atom, and here let me make it very clear, for our visibility we are showing the 2 atoms at 2 different corners, but in reality both the atoms are in contact with each other. Both the atoms are in contact with each other. The primitive unit cell, as I told, that the atoms are ions are arranged in at a corner. This is how we are showing it. This is what in these slides also that we have seen. But in reality, it is like one atom is in contact with another atom, and in this is how the square of one layer will be formed. Then again on top of it another 4 will be placed, on top of it another 4 will be placed, then you will get a cube. Then the line joining of centers of 2 such cubes vertically and horizontally, when you take, that will give us the length of an edge of a cube. So what I mean to say is, if you consider that this length as A, and if you consider that this is equal to R, that is the radius of the sphere, each atom or ion, we are showing it as one sphere, each sphere is an atom or a molecule or ion. Then if this is the edge length of the cube, then in the primitive unit cell, A is equal to 2R. In the primitive unit cell, A is equal to 2R. That means 2 atoms are in contact with each other like this, right. So when 2 such you are having, they are in line, another 2 you are taking it like this, these are also in contact, right. So, then this is 2r, this is 2r, this is 2r. Any edge length if you take, then A is equal to 2r. Another 4 if you keep on above these 4, then what you will get is a cube like this. So, here even though for our convenience we are showing it like this, does not mean that these 2 are not in contact. What you have to take into consideration is that these 2 are equal to, or these 2 are in contact with each other, they are in contact. So, A is equal to 2r. This is what is the primitive unit cell. And so, in the primitive unit cell, straight away you can say that A is equal to 2r. Then, in the case of body center unit cell, that what we will see it now. In the case of body center unit cell, what will happen is the 2 atoms along the edge are not in contact. 2 atoms along the edge are not in contact. How that it happens, that we will see next. So, body centered cube, BCC. BCC means in this atoms are placed like this. These 2 are not in contact. In the primitive unit cell, these 2 are in contact. Now, these are not in contact. Point number 1. Point number 2, this is layer 1, first layer, and in the second layer, this is another atom. This is second layer. In layer 2, atoms are placed on the base of set of 4 spheres. So, these are 4 spheres of layer 1, 4 spheres in layer 1. So, these are the 4 spheres of layer 1, on top of them 1 sphere is kept, that will form the second layer, and third layer spheres. In the third layer of spheres are in identical position to those in layer 1. That means another 4 spheres are kept it like this. So, these 2 are not in contact, these 2 are not in contact. So, this will form say 1 layer, this will form like 1 layer, or this will form 1 layer vertically or horizontally, whatever the way we take. Then at the center of the body, this one will be there, and these 3 will be in contact diagonally. Now, so if you keep another 4, when these 2 are not in contact, but if you keep another 4 over here, then 1, 2 and the third one that is coming on this will be in contact. So, these 3 are in contact. So, in this case, if this is edge length A, what you can write is that A is greater than 2r, this is again r. So, this A is greater than 2r, or another straight away what you can write is that if this is your body diagonal, this is your body diagonal, the square of this body diagonal is equal to square of this plus square of this, right? Right? So, now if you take this radius as r, this diameter is 2r, then this radius is r, total 4r, and this is 2a square, and this is a square, this is square of this if you take it as a square, and this if you take the square of this as 2a square, then 4r square is equal to 3a square, or 2r is equal to root 3a, or a equal to 2r by root 3, or r equal to root 3a by 2, whatever it is. Okay. So, 4r square is equal to this a square plus 2a square, total 3a square. So, 4r square is equal to 3a square. So, 2r equal to root 3, or a equal to what do you call 2r by root 3, or r equal to root 3a by 2. So, this is what? So, in the case of simple cubic unit cell, a is equal to 2r, but in this case a is greater than 2r. This is body centered cubic unit cell, right? Then next is face centered cubic unit cell. What is face centered cubic unit cell? The face centered cubic unit cell is, as already we told, it is the lattice points. The lattice points means the positions at which the atoms are placed. The lattice points are corners and face centers. That is the arrangement. Now we discuss the face centered cube.